Okay, so one of my main topics in my research career has been to study atomic and molecular negative ions, and I just thought with a few 2 minutes here about telling why I think they are interesting. So basically, Henrik Hartmann this morning showed the typical energy level diagram of an atom, and with all the ground state and all the excited states. And to point out, then for an atom or a positive ion, you always have a long range 1/r potential. If you form a negative ion, think about H-. You take a neutral atom and you attach an electron, which basically means that there is no long range force. And conceptually, you can actually think about this as the square well potential that is the first step in the quantum physics class. And if you then go into the properties of this square well potential, you know that there is a limited number of bound states. And also the number of states depends on the depth and width. And it turns out that this the binding energy here is so small. So typically a negative ion has only a single state, maybe possibly some excited fine structure components. So if you then, I'll do here. So the properties of negative ions differs considerably from atomic systems. The binding energy is typically an EV. There is few, if any, excited states. And there is only 4 elements where people have found an optically allowed transition. It's osmium, cerium, lanthanum, and thorium. So there's a lack of optically allowed transitions that make spectroscopy more complicated. But the key reason to why I study them from the atomic physics point of view is that the whole existence of these systems depend on the electron correlation. The 2 electrons in the H- need to be on opposite side of the nucleus on average to be able to be bound. So therefore, you cannot, if you use Hartree-Fock model, H- is not stable. You need to include electron correlation in the full model of the system, and therefore negative ions are excellent systems to test atomic theory. And I will start out by pick one experiment. We probe the properties of a negative ion, and the element of choice I will present here. I've studied maybe 30 different negative ions, but the choice here is astatine, and this is the PhD work of David Leinbach and Julia Sundberg. And astatine, it's down here. Maybe you haven't heard about this element. It's the heaviest halogen. It's the least abundant element on Earth. There's estimated that there is about 70 milligram in the crust of the Earth, not per something, but per Earth. And it decays through an alpha decay. And simply due to this extreme rareness, there is very little known about the chemical and physical properties of this element. But it is used in a cancer therapy that is called targeted alpha therapy. And the reason, so basically what people do is that they put an astatine atom on an antibody that binds specifically to cancer cells. And the reason to use astatine is that it has a lifetime that is suitable, it has an energy that is suitable, and the products are non-toxic and non-radioactive. So it's an excellent choice for this therapy. But people don't know the chemical and physical properties. So therefore we decided to measure this electron affinity of this element, to follow up a previous work at CERN where they studied the ionization potential. So this one, the work I will present was done at CERN, that you know of. At CERN, one facility is called Isolde, where they take the beam, not injecting into the LHC, but instead they smash it into the target, where you produce basically any isotope that exists. Then with an advanced system, you extract the ions, you mass select them, and this is an overview of this. And then we have a big laser system to study them. So to make a very complex experiment very short, from the proton beam we extract, we get a beam of astatine. And what we do then is that we take our here's iodine, but because we also study iodine, but we take the negative ion beam, we deflect it into a Faraday cup. And then we apply a laser beam over this range. And the idea is simply that we apply a laser beam and look what energy we need on the photons to break up the system. The problem is that we need to do it collinearly because there's very few. Typically, when we do the experiment, the number of ions in the interaction region, the density of the target is 0.01. So in most cases, we have no ions, and in some cases, we have one ion in the range. If we now photodetach it, it will continue straight forward, so the detector will sit in the beam of the laser beam. Therefore, we have developed a detector now consisting of a quartz plate covered with graphene. This means that the laser beam can pass through, but neutrals impinging produce secondary electrons that we detect with the channel electron. Just to give you the number, we have roughly 10 to the 14 photons in a pulse, and we want to detect 0.01 atom. And this is the detector system that we call Gandalf. That's the name of this. That was built by Julia Sundberg in my group. So what we then did in the experiment, we simply tuned the wavelength, and we looked for the number of neutralized atoms, and we could see a very nice onset of this. And this is described what's called the Wigner Law. It's a very simple analytic expression. We can make a fit and determine the position basically corresponding to the photoelectric effect. Then we repeat this, do it both with the laser beams co-propagating and counter-propagating. We get large Doppler shifts, but taking the geometrical mean, we can cancel them to all orders, and we can extract the electron affinity. This has been studied in a lot of different theoretical work before. And here you can see the value that we came up with. And we, in our Broszewski's group, did the calculation, had a very nice overlap. And I should point out here that this is an ab initio, so you see 2.415, and they got 2.414. This is ab initio calculation with a very relativistic many-body system. And with this affinity known, and since the ionization potential was known before, we could extract the electronegativity, which is a very important number in chemistry that is needed for the chemist to understand the ability of this element to form molecular bonds. And just to finish this part of the talk, here you can see the periodic table with the electron affinities, where I measured quite a few. The blue ones are the ones that have a positive affinity that has been measured, and now we added this the value of astatine. And you can see this complete different story, because the blue ones are the ones that exist and have been measured. Light gray ones are predicted to not form negative ions, like the noble gases. Green ones are predicted theoretically to form negative ions, but have not been studied. And the gray ones has neither been experimentally nor theoretically investigated. So it's a little bit like a terra incognita still in the very fundamental properties of these systems. With that, I move to the second part of my presentation. Well, I say this was published in Nature Communications last summer. With that, I go to the next thing, and now I will present an experiment where we actually make use of the negative ions to produce ground state atoms. And we did this on carbon minus. Carbon has an affinity of 1.26. By using a femtosecond laser, we can photodetach the carbon minus and produce the ground state carbon. But now, if we have a short laser pulse that has a Fourier transform that is smaller than the width here, we produce a superposition of those states. So this is the unique thing. We can produce an atom at a certain time with a certain phase relation between the fine structured components. So when you do that, we form a wave package consisting of a superposition of the three fine structure components, looking like this. But since they have different energies, they will have different time evolution, which means that you can see in this. No, okay. This will, I will show it in the next slide. Oh, there it comes. So what will happen here is that as time evolves, the wave package that we have produced is evolving, changing its spatial distribution. What we then do is the following, that we've produced the ground state. Now we apply a second laser beam that photoionizes carbon with a multiphoton ionization. And then we detect the electrons coming out, and we of course see both electrons from the first step and the second step. And we detect them with a VMI detector, where we basically can have both energy and angular resolution. And here you can see this VMI picture taken when we apply the two laser beams at the same time. This blob, this signal here in the center, that is the photodetachment, the first electron. And the second electron is not coming out now because the laser polarization is in this direction and there is no density in the wave package along the z-axis. But as time evolves, the wave package is changing and we now have a density along the z-axis and we start to emit electrons along the z-axis. And taking one further step, we get a huge signal along the z-axis. And I should also point out here that, so this is the laser polarization direction. This distance from here to here is the energy. And out here, where we see the signal disappearing, this corresponds to an excess photon detachment of 40 electrons. So it's an enormous amount of photons that we have absorbed. Now, of course, we can just put this together. And now we can basically, let's see if this can probe this wave package evolution with, but what we then do is, of course, that we project that onto a screen sitting up here. And this is the results of that, what we see. So you can see here the clock is running here. So you see like a 5 picosecond movie where we can actually probe how the wave package is oscillating in this system. I think it's a very beautiful demonstration of the tools that we can use with a femtosecond laser. And here, the negative ion was not really the concept, but we use the negative ion because you have a loosely bound electron that easily can be removed at a certain time to produce a specific state of an atom. Okay, next thing is a follow-up of this. And this was done by Mikael Eklund, who was also a PhD student of mine. And he had actually had a mathematical background. And in what I showed you before, we basically have the ion beam and the laser beam, and then we detect it in the third direction. So basically what you saw was we created a electron wave, and then we project that on the detector. So we have a real three-dimensional emission, and it goes to hit a two-dimensional surface. And he was thinking about this and said, but couldn't we use tomography to make a real three-dimensional image? And of course, what you do then is that you take images for every angle of the laser polarization. So basically in the tomography, you rotate your detection and measure it at all angles. And then by using mathematical tomographic routine, you can backtrack and extract the real three-dimensional structure. And here you can see 4 images at 4 different angles of the polarization detected. So these are 4 images at different angles, 4 different projections of the three-dimensional system. And we did this, and here you can see a movie. And let's see. No. Yeah. Where we run the angle and as we rotate. So this is actually the experiment. And then after reconstruction, we can then come up with, and I take this once more. So this is what we see, the different images. That's the movie. And if you backtrack that to the real three-dimensional scheme, you get this. And here you can make a cut and make any observation. So here you can see how we have made a cut to demonstrate that we actually see. And what you basically see here is that this is where you emit the electrons with sufficient number of photons. Here, the caps is when you add an extra photon. So you have excess photon detachment of one extra photon. I think this is a beautiful demonstration of the tool that you can apply here to really get the demonstration of how an electron wave is emitted in the photoionization or photodetachment process. With that, and this was published last year in Fistral A. Now I come to the final topic of my talk, and that is work we do, and this was mentioned before. And here I come now to photodetachments using electrostatic storage rings. And the work presented here is the main work of Erik Bäckström and Moa Christiansson. And what I will present here is what Henrik Hartman pointed out, the Desiree, the double electrostatic iron ring experiment at Stockholm University. And this is a national facility. So if you have an idea of experiments that could be conducted here, you're most welcome and submit a proposal. And if it's accepted, it's free of charge to do the experiment. The whole concept here is that you start with an ion beam, ion source here. You mass select it, you bend it in, and you go into this storage ring that is in a cryogenic environment. Assume that you have positive ions that you inject and you circulate them in this ring. Here you have another source, and here you can put negative ion source, mass select, and inject in a second ring. And since there are different charges, by having a merger electric field, you can merge the two ion beams. So the two ions fly on a 2 meter distance collinearly, and then you demerge them again. They can circulate in here. And if you change the potential of the tube that is surrounding this region, you change, then the positives will be accelerated and the negatives will be decelerated, or vice versa. So that means that you can change the collision energy between them, and you can do this down to 0 energy. So the main purpose of this ring is to study collisions, basically neutralization. For instance, H minus colliding with H plus, forming H plus H. So basically one electron jumps over. This facility has some unique properties. The whole system the whole chamber is kept at 13 Kelvin. That gives a pressure of 10 to the minus 14 millibar. So it's about 10,000 H2 atoms per cubic centimeter. The storage energy is about 10 to 30 keV. And since it's electrostatic, you can store relatively heavy systems. So this is possible to use for atoms all the way up to large clusters or biomolecules. It took about 10 years to construct this, and at a cost of about 50 million euro. And it is like a few years ago, it was basically completed, and now it's open for operation. Here you can see the ring during the construction phase. So basically, this is the merging section. The ion comes here and fly here, and this the way, or they come in this way and fly here. Here you can see when it's slightly more closed in. Now all the electrons are placed here. These are cryogenic coolers for pumping. And here you can see now, basically, so I say the whole chamber, I mean, this is like 3 by 8 meters. It's one vacuum vessel with all the feed-throughs coming in. you put on the lid, and it takes about, if we need to attach one more screw here, it takes about 1 month. So it is a little bit like space science, because to open it, we need to heat it up, and that takes about 2 weeks, lift the lid in 1 day, attach the screw in 1 minute, put the lid on, tamp down, and cool. That takes another 2 weeks. So basically, the operation is that the idea is that we only open this facility in the summers. And I will just show, and I've been using this as a single experiment, and I will just present a little bit about that. So the first experiment we did with the ring was basically to study sulfur minus. And sulfur minus has a bonding energy of 2 eV. And there's a fine structure splitting between the 1/2 and 3/2 states. What the way we produce the ions is in a sputter source. So basically, we have a solid target, and we shoot cesium ions of 10 kV into the target, which means that the internal temperature is very high. So we make a very non-Boltzmann deviation from the Boltzmann distribution at the room temperature or the temperature of the ring. So when the ions enter the ring, you have a very high population in the excited state compared with the equilibrium state, which basically means that those will radiate. But since this is not a loud transition, it will decay by an M1 transition that is very slow. Now, the way to do the experiment is simply to apply a laser beam, exactly as we did with the astatine, and we put it in such a way that we photodetach the excited state, but not the ground state, which means that we can probe the population as a function of the time after injection. And here you can now see the time scale, and here you can see we apply the laser for about a second, about 30 seconds in between. So here you can see a blow up, and then we can see how the population in the excited states decays of the injection. We can make a fit here, and we can extract the lifetime. And in this case, we see a lifetime of 500 seconds, 503 seconds. So we basically, it's a time domain completely different from normal atomic conditions. And it all depends on that the extreme good vacuum, so we can store the ions for hours. So we can inject a bunch and keep it there for hours, and then we can inject a new bunch. And I will then just show you the very last experiment that we do here on this work. And this is, we're following up on a very old measurement from 1985, and that is to measure the electron affinity of oxygen. A problem with oxygen, well, if you saw the astatine experiment, there was a very nice zero background. But in oxygen, you have an excited fine structure component, which basically means that if you place, so this is the energy level of the ground state, the O minus, and the ground state of oxygen. And we basically want to probe from the ground state of the negative ion to the ground state of the atom. But when you tune your laser to this, the excited state will be photodetached, and that will be a far above threshold, giving a huge signal. So this is the experiment by Neumark. You see here that you had the signal. You see the scale here is like 100 counts, and it goes up to 120 over this small range. And all this here is the signal from the excited state. And when you scan, basically meaning here that here you scan from this state to this state, but you want to measure this threshold with high precision. Our idea then is the following. We inject the ions in the ring, and I said we can store them there for a long time, which means that we first apply a laser that photodetaches the excited states. So this is like a cooling, we get rid of the excited state. It takes about 20 seconds. When we have done that, then we scan the laser from here to go above and can look for the threshold. And here you can see from the scope, from a single scan, that here we go below the laser, we scan up above the threshold, and then we scan back down again below the threshold, and can determine the threshold with very high precision. This is more Christenson's thesis work, and we have the data, and here you can see our resolution compared with previous experiments of the same quantity. She's now finalizing the calibration to determine exactly where on this scale the value is, but clearly we make a 2 orders of magnitude improvement of the precision here by using the this cooling mechanism in the ring. And with that, I conclude and said that I hope I showed you that negatives are ions are fundamental system where there's a lot of things to learn. They are suitable models to study small quantum systems. And development of experimental techniques have allowed studies of radioactive isotopes, studies of fast processes, and study of slow processes. And with that, I would like to acknowledge, first of all, my 2 very dear Latvian friends, Uldis Bersiņš. Some years ago, he came into our lab, and we have collaborated since then. I was thinking now, I realized my son was newborn, and my son is now 32 years old. So it's a long time we've been working together. And very early, I came in contact also with Uldis. And I would also then thank the organizers, to point out that we have this collaboration where we actually have built a small ion beam apparatus called Riga, the Gothenburg Riga ion beam apparatus that is shown here. It was started to be constructed in Gothenburg and is now in Riga, and I just heard that it's in operation stage now. A great advantage with this one is that it has a charge exchange cell, so one can, for instance, produce helium minus, which is a very interesting element. And then I would just thank you, the other people I've been working with, and here you can see a snapshot of my group at one specific time. And with that, I thank you for your attention.
Thank you for your presentation. Maybe there are some questions. I see questions from Sun Svanberg, please.
Actually, my reaction was clapping my hands. But I just would like to say it was an excellent talk and a very nice endeavor in fundamental quantum mechanics and a deep look into these fascinating systems. Very nice.
Thank you.
Thank you. Are there any other questions? So I see no questions.